In this video, we're going to finish off discussions of Le Chatelier's principle in shifting equilibrium, talking about the impact of temperature, addition of a catalyst, and finally looking at a historically important example of Le Chatelier's principle in action, the Haber-Bosch process. So let's start with the impact of temperature. The impact of temperature on the position of equilibrium and shifting equilibria is unique because the effect is not on the reaction quotient, but on the equilibrium constant itself. The equilibrium constant is temperature dependent. In other words, it varies with temperature. Q is unaffected, of course, as we raise or lower the temperature, since reactant and product concentrations can remain the same as we do this. But K changes, and so temperature can cause the position of equilibrium to shift in accordance with Le Chatelier's principle. And we're going to do a little derivation to see how this works right now, and then develop some intuitive ideas about how temperature shifts equilibrium toward the end of this slide. So let's start with the temperature dependence of the equilibrium constant and how we think about that. That is based on the connection between the free energy change of reaction, delta G, the standard free energy change, that's what the little circle means, and K, that is based on the dependence of K on delta G. And if we unpack delta G as delta H minus T, the temperature delta S, we end up with the equation you see here. The natural log of K is equal to the entropy change divided by the ideal gas constant minus the enthalpy change divided by the ideal gas constant times the temperature in Kelvin. Now this essentially tells us how K varies with temperature, but to get an intuitive feel and to sort of move forward with appreciating how K varies with temperature qualitatively, it's helpful actually to differentiate this equation with respect to temperature and look at the sign, positive or negative, of dk dt. When you do that, I'll spare you the math of differentiating both sides with respect to temperature. You end up with dk dt is equal to the equilibrium constant itself, K, times the enthalpy change divided by the temperature squared. And with the temperature in Kelvin and the equilibrium constant being positive, what this tells us is that the sign of the enthalpy change is the same as the sign of dk dt. In other words, the rate of change of the equilibrium constant with temperature has the same sign as the enthalpy change. And this leads to some intuitive ideas that we're going to develop as we go through this table. So let's consider 4 scenarios involving either an endothermic or exothermic chemical reaction. In other words, delta H is either positive, as we see in blue, or negative, as we see in red. And we can imagine the temperature either increasing or decreasing and ask what happens to the position of equilibrium and whether a system in equilibrium will shift toward products or back toward reactants in response to this change. And of course here, I mentioned this earlier, the effect is on the equilibrium constant here, not the reaction quotient, because the reaction quotient won't change as we raise or lower the temperature, but K will. All right, so the first case, that's an endothermic reaction, and we're imagining the temperature increasing. Well, based on this equation above, with delta H positive, the sign of dk dt is positive. And what this means in terms of rates of change is, as we increase the temperature, the value of K increases. This creates a situation where Q is less than K, and the reaction thus needs to go in the forward direction, generating products and consuming reactants in order to restore equilibrium. So the reaction will go forward. So that's an endothermic reaction. With an increase in temperature, the reaction will go toward products spontaneously. Naturally, if the temperature decreases, well, the sign of dk dt is still positive, and so if the temperature goes down, K will go down. And in that situation, Q is greater than K, and the reaction will run backwards. Now let's think about an exothermic reaction. In this case, the sign of delta H is negative. The sign of dk dt is negative. This means that when T increases, as we see in this third line here, the value of K will go down. And Q will be greater than K as a result of this, and the reaction system will run predominantly in reverse. In other words, the rate of the reverse reaction will be greater than the rate of the forward reaction, and the reaction will end up running backwards, generating reactants and consuming products to restore equilibrium. And finally, of course, the opposite is going to happen for an exothermic reaction when the temperature decreases. In that case, K will become greater than Q, and the reaction must run in the forward direction to restore equilibrium, generating products and consuming reactants. So all of this stems from the connection between the sign of the enthalpy change of the reaction, delta H, and the sign of dkdt, and the fact that they match. So exothermic reactions with negative delta H have negative dkdt, and endothermic reactions with positive delta H have positive dkdt. Now, intuitively though, there's a connection here between temperature, heat, and the direction the reaction goes. And this is a little bit hand-wavy, but it'll get the job done when you're solving problems and applying Le Chatelier's principle kind of in a practical sense, which is why I mention it here, with the typical caveat that we really can't think in the way we're going to do in a robust sense, right? It's not exactly 100% rigorous, shall we say, but it gets the job done. And the idea here is to think of heat either as a reactant for an endothermic reaction or a product for an exothermic reaction. Thinking in those terms actually allows us to harken back to the concentration effects that we talked about when we first introduced shifting equilibria, arguing that when we increase the temperature, we're adding heat. For an endothermic reaction where heat is a reactant, quote unquote, that's going to push the reaction toward products, and vice versa if we're cooling, lowering the temperature, and removing heat. And we can make an analogous argument for exothermic reactions in which heat is a product. Adding heat will push the reaction system back toward reactants, and removing heat will push the system, pull the system in a sense toward products. So it's a little bit hand-wavy, but it will get the job done for you when you're solving problems involving temperature and shifting equilibria. Very briefly, let's talk about the impact of a catalyst on the position of equilibrium. This is going to be very brief because all I'm going to say is there is no impact of the addition of a catalyst on the position of equilibrium. Catalysts affect the activation energy of the reaction. We can see that here with the blue reaction profile having a lower activation energy than the red one. But notice that the same delta G is happening in both cases. With the same change in free energy, the equilibrium constant is the same. And so neither Q is affected nor K when we add a catalyst. And so catalysts do not impact the position of equilibrium, and we can't use a catalyst to shift an equilibrium toward products or toward reactants. This is an important intuition, particularly if you'll go on and take more advanced chemistry courses. A catalyst, a true catalyst, cannot make a reaction that is thermodynamically unfavorable favorable. We can't use a catalyst to get more product out of a reaction than we would have in the absence of the catalyst. Finally, I want to talk about this historically important application of Le Chatelier's principle in the Haber-Bosch process. So the whole idea behind the Haber-Bosch process involves the production of ammonia, NH3 gas. And that's a product in this chemical equation that we see at the top of the slide, 2NH3 gas. This is an exothermic reaction, and so we can think about temperature effects on the position of equilibrium to shift it toward products. And it's a reaction that has a net consumption of moles of gas. We go from 4 moles of gas total on the reactant side, 1N2 and 3H2, to only 2 on the product side. And again, we can take advantage of that using ideas about volume and partial pressures that we've seen previously. And so an apparatus for producing ammonia by taking advantage essentially of Le Chatelier's principle is shown here on the slide. And I've highlighted some key areas where the design of the apparatus really leverages shifting equilibria. So first, there's a compressor. The N2 and H2 are fed into a relatively small volume via a compressor, and this encourages consumption of those moles of gas to produce products which come out as a smaller number of moles of gas. There's a heater, which is going to increase the temperature. Now, this would seem to shift the reaction actually backwards, but there's also a kinetic effect here, right, where we're accelerating the reaction. And we remove the product. There's refrigeration on the far side of the apparatus. The NH3 condenses out. As we remove that product, that encourages the generation of more NH3 in the actual reactor. We can also see there's water cooling there, which will encourage the ammonia to condense out as well. So Le Chatelier's principle in action, the Haber-Bosch process, and in the absence of all this, the equilibrium is much more balanced between reactants and products. This reaction doesn't heavily favor NH3. But with these interventions, we can get essentially as much NH3 as we want out of a mixture of N2 and H2 gas.